Well, here are the problems on heat and transfer of heat. Question number 1. It talks about heat transfer into a mass. Remember that the equation for heat transfer is quantity of heat is equal to the product of mass, the specific heat, and the change in temperature. So Q is mc delta T. C is the constant for each material. And in each case you're asked to find the final temperature. So we will find the change and add it to the initial. The first case, it's 1 kilocalorie, that's Q. Mass is 1 kilogram for each of them. The specific heat of water is 1 kilocalorie per kilogram Celsius. That gives 1 degree Celsius. And therefore the final temperature is 20 plus 1, 21 degrees Celsius. Same thing for the second. The only difference is going to be with the specific heat, because it's a different number for each material. Concrete is only 0.2 kilocalories per kilogram degree Celsius. So concrete gets heated up a lot faster than water does. So remember that the smaller the specific heat, the bigger the rise in temperature. C is about steel. In this case, the specific heat is 0.108. Again, kilocalorie per kilogram degree Celsius. Gives 9.26. So the change is 20 plus 9.26, which is approximately 29.3. In D, it's mercury. .033. It's a metal, so it has a very small specific heat. That means the increase in temperature will be higher. As you can see, it's 30 degrees Celsius, therefore the final is 50 degrees Celsius. So I hope you understand that a smaller specific heat means a bigger change in temperature. And so water is one of those substances that has a very high specific heat, and therefore the increase in temperature of water is going to be really small. And that's one of the reasons, the main reason I should say, as to why water is used in the radiators of cars. Now that can be a conceptual question, the importance of water. And that's another reason why in nature you see that even on a very hot summer day, the temperature of a lake doesn't go up by that much. Why? Because number one, its specific heat capacity is very high. Number two, of course, there's a lot of water in it. Okay, that takes us to the second question. Food packets are always labeled in calories, but remember that it's actually kilocalories. And it's found by calorimetry techniques, in which the food is burned and the amount of heat transfer is measured. Here it's talking about how many kilocalories per gram are there in a 5-gram peanut. If the energy from burning it is transferred to 0.5 kilogram of water held in a 0.1 kilogram aluminum cup, causing a 54.9 degrees Celsius temperature increase. And it says compare your answer to the labeling information on the package. Okay, Q is mass times specific heat times change in temperature. But in this case, you have two substances. You have the food and you have water. You have water and the aluminum. Both of them are going to have heat absorbed, and the change in temperature is common, so delta T is taken out. Mass of water is 0.5 kilogram. Specific heat of water is 1 kilocalorie per kilogram degrees Celsius. The mass of aluminum is 0.1 kilogram. Specific heat of aluminum 0.215. I don't want to keep saying that unit again for specific heat. And the change in temperature is 54.9, of course, and when you calculate, you get 28.63 kilocalories. But now that means it was the same amount of heat produced in 5 grams of peanut. So we're going to find the quantity of heat in 1 gram of peanut, because that's what the question says. The question said, how many kilocalories per gram? And so we'll have to divide by 5. That gives us 5.73 kilocalories per gram. So for every gram of peanut that you eat, you get 5.73 kilocalories. And does this agree with the information on the package? Well, what does the package say? The package says 33 grams has 200 kilocalories. So for 1 gram, it's 200 by 33. That gives 6 kilocalories per gram. So it is consistent and it agrees. Okay, in this third question, how much heat is required to raise the temperature of a 0.75 kilogram aluminum pot, which contains 2.5 kilograms of water, from 30 degrees Celsius to the boiling point, and then boil away 0.750 kilogram of water. So now there are two things that should take place here. First, heat is going to be required to increase the temperature from 30 to 100 degrees Celsius. And then heat is required to make it undergo the phase change, that is for water to boil. And the formulas in these two cases are different. For heating, it's the product of mass and specific heat and change in temperature. And again, there is aluminum and water. But the last quantity which I'm writing now, that quantity talks about the heat required for the change in phase. So heat required for change of phase is given by an entirely different formula. It is the product of mass and the latent heat. Mass and the latent heat. In this case, the latent heat of water. So the mass of aluminum multiplied by the specific heat of aluminum, and the change in temperature is 100 minus 30. Always remember, it's the higher temperature, take away the lower, plus the mass of water, specific heat of water there, change in temperature is the same, plus the mass of water. Now that is, I had to write, let me correct that. It's actually 0.750. 0.750, because that's the only amount of water that is to be boiled away. 539 kilocalories per kilogram is the latent heat of water. When you do all those calculations, you get 590.5 kilocalories, approximately 591. And second part says, how long does this take? If the rate of heat transfer is 500 watts. Power is Q by T, so time is Q by P. Q is 591, power is... Okay, now there's a problem. You have to change kilocalories into joules. How do you change? Multiplying by 4186. So you have 591 times 4186 divided by 500, which gives you 4.94 times 10 to the 3 seconds. Number 4. A 0.250 kilogram aluminum bowl has 0.8 kilogram of soup. Both are at 25 degrees Celsius and it's placed in a freezer. What is the final temperature if 377 kilojoules of energy is transferred from both of them, assuming that the soup's thermal properties are same as that of water? Which means the specific heat of soup is considered to be the same as that of water. Most of it is water anyway. So now heat is going to be removed from both, from aluminum and then soup. And the change in temperature is the same. That's why I have written it common there, delta T. Okay, so make delta T the subject. So you go 0.250. That is the specific heat of aluminum which will be given, plus the mass of soup, times the specific heat of water, times change in what's that? Okay, I should write Q. So that's Q, and remember that the change in temperature here is 25 because I'm finding the quantity of heat for it to go from 25 to 0. Okay. So that gives 21.34 kilocalories. Okay, that's Q. But 377 kilojoules has been removed. Only 21.34 has been used for this decrease from 25 to 0. Are you with me on that? So the amount of heat remaining is 377 take away 21.34. Which is 355.66 kilocalories remain. And I want to show you that the remaining amount of heat is not enough for the whole soup to be frozen, because the latent heat of water and that of soup is 539 kilocalories per kilogram. And if you had to freeze the entire soup, you would need this much of heat, which is not available. You didn't remove that much. Therefore, the answer is the whole of the soup did not freeze, and therefore, until all of it freezes, the temperature will not go below 0 degrees Celsius. So the final temperature is 0 degrees Celsius, and that's the answer. The final temperature is 0 degrees Celsius, which is 273 Kelvin. It will not decrease below that. That brings us to number 5. Here you have a 0.05 kilogram ice cube at negative 30 degrees Celsius placed in 0.4 kilogram of 35 degrees Celsius water in a well-insulated container. So the mass of the container is not given and none of its properties. So we are assuming that the container does not absorb heat. Therefore, the heat gained by ice to reach 0 degrees Celsius from negative 30. That is just heating up of ice, and then after that the heat gained by ice to melt. So the first one, heat gained by ice to reach 0, is its mass times, now that must be the specific heat of ice, not water. Specific heat of ice times change in temperature plus heat gained by ice to melt is mass times latent heat. Okay, the first part, that's the mass, kilograms. Now you have the specific heat. Okay, again, I should put the specific heat of ice. And the specific heat of ice is exactly half of that of water. So that will be 0.5. So that will be 0.5 kilocalories per kilogram. And the change in temperature is, of course, 30 degrees Celsius. Higher minus lower. Plus mass of ice is that 0.05 times latent heat of ice is 79.8 kilocalories. Okay, and that gives 4.74. Okay, I'm changing again. 4.74 kilocalories. And now after all the ice is melted, you have water, right? So now you have water at 0 degrees Celsius and you have hot water at 30 degrees Celsius. Is it 30? 35. Oh, sorry, that 35. So now you're mixing water with water. So heat lost by hot water is equal to the mass of water, which is 0.4 times the surface heat of water times the change in temperature. Which is 11.85 degrees Celsius. So understand that by the time ice was heated up and ice melted, the temperature of water already went from, it went down from 35 degrees Celsius by 11.85. So now you have water at 0 degrees Celsius, which is mixed with water at 23.15. Where do you get that? That's 35 minus 11.85. So heat lost by the hot water is equal to heat gained by the cold. So on the left hand side, I have the mass of cold water, 0.05, times the change in temperature. I'm going to take it as TF as the final temperature. So TF minus started from 0. On the right hand side, I have the heat lost by hot water. And here the change in temperature is going to be 23.15 minus TF. Always take maximum minus minimum. Bigger minus the smaller. Now this question has 3 parts and you got to be really careful when you do this. Therefore the final temperature is going to be 20.6 degrees Celsius. In the 6th one, you have to find, this is to do with conduction of heat. You have to find the rate of heat conduction. The word rate itself means heat lost in 1 second. Through the house walls that are 13 centimeter thick and the thermal conductivity is twice that of glass wool. Assume there are no windows or doors. The surface area of all the walls is 120 meters squared. Inside surface is at 18, outside is at 5. Okay, the formula for conduction is Q by T. Q is the quantity of heat conducted, T is time in seconds, K is thermal conductivity, is a constant for each material, A is the surface area, T2 and T1 are the temperatures, again bigger minus the smaller. By D is the thickness of the wall in this case. And K is twice that of glass wool, so 2 times 0.042. Area is 120 meters squared. Temperature difference is 18 minus 5. Divided by the thickness in meters is 0.13. And when you do that, you get 1.01 times 10 to the power 3 watts. And how many 1 kilowatt room heaters would be needed? Just one of them, because the heat is being conducted at the rate of approximately 1 kilowatt. So just 1 kilowatt heater is required. Sixth one. Oh, that's a repeat. Okay. The seventh one. Now a fireworker runs across a bed of hot coals without sustaining burns. Calculate the heat transferred by conduction into the sole of 1 foot. Given that the bottom of the foot is a 3 millimeter thick callus with a conductivity at the low end of the range for wood, which will be given as density is given. The area of contact is 25 centimeters squared. Temperature of the coals is really high, 700 degrees Celsius, and the time in contact is 1 second. So we have to find the quantity of heat conducted in 1 second. In 1 second. First, let's find the mass of the 3 millimeter thick callus. Mass is volume times density. Volume is area times thickness, isn't it? Now, area here is 25 in centimeters squared. When you change it into meter squared, it's times 10 to the negative 4 meter squared. Okay. Thickness is in millimeters. So 3 times 10 to the negative 3 meter. Density is 300. And that's in the proper units, kilogram per meter cube. So the meter square cubes get cancelled and you get the mass as 2.25 times 10 to the negative 5 kilograms. That's just the mass of that small part of the foot. Okay, now heat conducted is Q by T. Q by T is equal to Ka T2 minus T1 by D Q. That's K, which will be given. Area is 25 times 10 to the negative 4 meters squared. Difference in temperature 700 minus 37, because 37 is the normal human body temperature. So the coal is at 700 and the normal temperature human body is 37. Divided by the thickness, which is 3 millimeter. Okay, and so you get 44.2 joules. And the temperature increase will just be given by MC delta T. Now you take the mass, which is 2.25 times 10 to the negative 5 times the C is 3500, again given. Change in temperature is what we're trying to find. So make that the subject. And it's only 1.68 degrees Celsius, which is small enough for a person to walk on burning hot coal. Okay, this question is about reducing the heating and cooling costs by adding extra insulation in the attic of a house. This house already has 15 centimeter fiberglass in the attic, and you are adding an extra 8 centimeter. And so by what percentage would the heating cost drop? The dimensions are 10 by 15 by 3. Ignore air infiltration and heat loss through the windows and doors. Now you have to remember that there are several areas here from the geometry. You know, it's 4 walls. You have the floor and then you have the ceiling. Okay, heat lost. So 2 times 10 by 3, that's the dimension of one wall. 2 of them. And then the 2 other walls are 15 by 3. Plus that is 10 times 15 is the floor. Oh, why are we not considering the attic? You will see now. So I've not considered the ceiling yet. I'm taking the ceiling separately because when you add 8 centimeter, it's only that part that is going to change. Okay, we do not know the change in temperature. We'll leave it as delta T. So the first number is 84 plus 42. And see what I did. I've taken it. Okay, not yet. Now understand that this is taken for 1 Kelvin. So that means I've assumed that delta T is 1 Kelvin. So we're finding the heat conducted for 1 Kelvin change. Now on adding 8 centimeter of extra insulation, only one term, the second term changes. So the first term is still 84 plus the second term becomes 0.042 times 10 to the 15 by 0.23. See, you see the difference? In place of 0.15, now you have 0.23 because 8 centimeters has been added. And again, we're looking at it per Kelvin. This number happens to be 27. So now you get 111 in place of 126. So take the difference. To find the percentage, take the difference divided by the original, which is 126 times 100, and that gives you 12%. So that's a big drop. In the 9th question, it deals with the human body and what is the rate of heat transfer by conduction through the body's tissue. So it's a direct question with the tissue thickness given. The change in temperature is 2 degrees Celsius and the area of the skin is 1.50 meters squared. How does this compare with the average heat transfer rate to the body resulting from an energy intake of about 2400 kilocalorie per day, which is from the food that you take, and no exercise is considered here, which will complicate matters. So conduction, Q by T, Ka, T2 minus T1 by D, K is 0.2, area is 1.50, change in temperature is 2, that is the change in temperature, so it's T2 minus T1, and D is 0.03, the tissue thickness in meters, which gives 20 watts. And the daily intake, this is per second. Watts is per second, so you have to multiply by 86,400 because that's how many seconds are there in one day. So 1728 kilojoules per day. Kilojoules, remember. And from the food intake, you get 2400 kilocalorie, which has to be changed into joules. Changed into joules, so that will be 4186 joules per kilocalorie. Okay, and that gives 10,050 per day. So what part of it is being used for conducting out is just 1728 divided by 10,050 times 100, because we need it as a percentage, and that's going to be 17.2%. Okay, I have not shown the 100. Let me just write it down. There should be times 100, so you get it as a percentage. Which brings us to the last question. At what net rate does heat radiate from 275 meter squared black roof for a night? When the roof's temperature is 30 degrees Celsius, surrounding is at 15, emissivity of the roof is 0.9. Now, this is the third part of the chapter, and here we're talking about radiation. And the formula for radiation, heat radiated per second, so Q by T, is E sigma A T2 raised to 4 minus T1 raised to 4. Let me just explain the terms. Q is the quantity of heat radiated, T is in seconds, E is the emissivity, sigma is called Stephan's constant. It's always 5.67 times 10 to the negative 8. It will be given to you But remember, it does not depend on the material. What depends on the material is the emissivity. For a black object, what is the emissivity? It's 1. And A, again, A is the surface area. T2 and T1 are the temperatures. In this case, emissivity is 0.9. Sigma is 5.67 times 10 to the negative 8. Those are the units of sigma. The area, 275 meters squared, is the area of the roof. Oh, remember that temperature must always be in Kelvin whenever you use this formula. Must have to be in Kelvin because you're not dealing with a difference in temperature. Do not forget that. Temperature has to be in Kelvin. So you get 21.7 watts. Wow, I thought we had finished. There are 2 more questions. 11th question. The sun radiates like a perfect black body with an emissivity of exactly 1. Okay. Calculate the surface temperature of the sun, given that it is a sphere with the radius and that it radiates 3.8 times 10 to the 6 watts into 3-dimensional space. How much power does the sun radiate per square meter of its surface? And how much power in watts per square meter is that value at the distance of the earth? Oh, that is called the solar constant. Good question. Okay. And okay, this one, the sun radiates like a perfect black body, excuse me, with an emissivity of exactly 1. Calculate the temperature of the sun. Okay, I think I read the question one time. And here, we use the formula for radiation. Q by T is sigma E A T raised to 4. Make T the subject. You're going to have to take the 4th root, which will be written as raised to 1 by 4. Another thing is to note that 4 pi r squared is the surface area of a sphere. So that is the surface area of the sun. Q by T, that is 3.80 times 10 to the 26. That's the quantity of heat in 1 second. And then you have sigma. E is 1, so I'm not writing that. And then 4 pi times the square of the radius. 7 times 10 to the 8 squared. Whole raised to 1 by 4. When you calculate that, you get it as 5.74 times 10 to the 3 Kelvin. In the B part, how much power does the sun radiate per square meter of its surface? Power. Power is Q by T. And it's per square meter, so you got to find P divided by A. And that would be P divided by 4 pi r squared. So we have the power, that is the energy radiated per second, which is 3.80 times 10 to the 6, divided by 4 pi r squared. And so from each meter squared, the sun radiates 6.17 times 10 to the 7 watt per meter squared. In the C part, how much power in watts per square meter is that value at the distance of the earth? So now you have to imagine a sphere which has the radius equal to the distance between the sun and the earth. And therefore all of the energy radiated by the sun falls on the entire area, which is 3.80 times 10 to the 26, divided by 4 pi times the distance squared. So now it's 1.50 times 10 to the 11 squared. That gives 1.34 times 10 to the 3 watt per meter squared. And by the by, this is called the solar constant. And now finally we come to the last one. In this question, as you see it, a shirtless rider, not a rider, under a circus tent feels the heat radiating from the sunlit portion of the tent. Calculate the temperature of the tent canvas based on the following information. The shirtless rider's skin temperature is given 34 degrees Celsius, emissivity 0.970, the exposed area of the skin 0.4 meter squared. He receives radiation at the rate of 20 watts, half what you would calculate if the entire region behind him was hot. The rest of the surroundings are at 34 degrees Celsius. Okay, in the first part, using the formula for radiation, we have Q by T is equal to sigma E A raised to, A by 2, T2 raised to 4 minus T1 raised to 4. Okay, A by 2 because the problem says he receives radiation at the rate of 20 watts, which is half of what you would calculate if the entire region behind it was hot. And so when you substitute the numbers after rearranging for T2, which is going to be a tough job, because first you got to keep this here, take all these terms to the denominator, which you see now down here, and then you have to take this to the other side, which will make it plus T1 raised to 4. And finally, you have to take the fourth power, or 1/4 power, and when you do that, this 2 here will go to the top and become 2 times Q by T. And then you got to substitute. So it's 20 watts is Q by T, sigma, you have E, emissivity, and you have the area. Okay, plus 307. Remember that temperatures have to be in Kelvin. 307, that is 34 degrees Celsius, surrounding temperature. When you do all that and calculate, you get 321.63 Kelvin, which is 48.5 degrees Celsius. In the B part, discuss how the situation would change if the sunlit side of the tent was nearly pure white and if the rider was covered by a white tunic. White reflects heat, and therefore in this case the temperature would be definitely lower and he would get less heat radiated onto him. Thank you. I hope you have understood how these problems are done. Take a good look at each question because you're going to see many of them in the exams.